So I ran across this problem on the internet, and a lot of people were able to get the right answer, but nobody really showed circuit analysis the way you might actually teach someone how to do it. So I thought I'd go through some methods for finding out what is the current through diode D3 in this circuit. And I'm going to use LT-Spice as a way to help verify the answer and show that what I'm doing actually makes sense. So first thing I did was redraw it in LT-Spice, and I used the DC operating point directive. And let me point out these question marks. So those are actual values that the simulation will arrive at, and having it displayed on the schematic so it's easier to see. And if I right click on one of those right now, see, it doesn't do anything. But if I run the simulation, so I'll get this table, and there's a lot of stuff in here, and it's always fun to sort through this table and try to figure out what's what. And so I close that, and these values show up. Now if I right click on it, there's this wildcard $. I call it a wildcard. It sets the alias to the voltage on the node you clicked. So if I were to click on this node that has nothing on it, it'll show me the voltage that's there relative to ground. Okay, and so that's what all of these things are. Now this one, if you go in there and you actually put in the expression for what you want it to show, you will get that. So I wanted this to show the current through diode D3. Now, with real diodes, you get an answer a little bit different, because the real diodes don't actually have exactly 0.7 volts for the forward voltage drop. This problem is assuming that all the diodes have exactly 0.7 volts forward voltage drop. So, but how do you approach this? Well, what I like, if I can, I like to redraw things where it helps me visualize what's going on better. So I moved ground to here, so I translated everything up by 5 volts. So I get 5 volts here, 10 volts there, and 15 volts here. Just makes it easier for me to visualize things. Then the next thing you want to do is which diodes are conducting. And you can kind of look at this and kind of get an idea that this diode is definitely going to be conducting because it's the highest voltage in the circuit, and you can kind of look at that and see it. The other ones aren't so obvious, but you might guess correctly that this diode is off and this diode is on. And to go over here, basically if you remove what is now D5 and D6, put in a 0.7 volt source for D4, and you can calculate the voltages at, I guess I had VA would be here, and VB would be here, and VC would be there. And so if I just showed you that, here's VA1. Okay. And VB1. And VC1 would be here. All right. And so you can see with this being 11 volts, D5 is not conducting current in the forward direction. This being 1.59 volts, D6 would be conducting current in the forward direction. And with real diodes, the question, what's the current through D3? Since these are simulations, every one of these is going to have a different reference designator, so just remember that as I go through this. So D6, which was D3, and using real diodes, you get 3.1 milliamps. It's a good answer, but it's not the answer to the problem as it was stated. So if you redraw this with the 0.7 volt drop as stated, then you get the right answer, 3.05. There must be some, within the accuracy of what the simulation does that makes it come out with this answer. Or you can, like I said, over here to the right, you can kind of just look at this and get the right answer, because you know that this is 4.3 volts, and you know that this is 14.3 volts. So you can calculate the current that goes through R7 and R8. And then, since this is 4.3 volts, you know that the current through R9 is 4.3 milliamps. So you just subtract this current from that current, and you get 3.05. And that's what this shows over here to the right. So that's, fine. You're done. You can almost just look at it. Oh, yeah, I get the answer. Well, that's fine. But the point is, I'm going to go through and show methods that you could use. This is a little too simple, but it's kind of nice that it's simple, because this will just show you how to get through if you had something more complicated, how to use these methods. So method one is superposition, and that's basically where you short circuit all the other voltage sources, or you open circuit all the other current sources. In this case, we only have voltage sources. So, and we only have two of them, because this is the final circuit. So there's really only two voltage sources that we need to do the analysis for. So the first half of this is you short V13 and you calculate this current. So you basically have 8K in parallel with 1K, and you end up with 4.8375 milliamps. Well, the simulation, again, has some accuracy things that are a little different, and you get a number that's essentially 4.8375 with some error, ridiculously small error. Then the other half of this is you short the other supply and calculate this current. Now this node is ground, so this current is going to be 14.3 divided by 8K, or 1.7875. This one's a little easier for it, I guess. It came out with exactly the same answer as it should be. And like I said, there's zero current in the resistor. So basically, there's zero current here. So all of the current going into this is 1.7875. And by superposition, since this one's going to the right and this one is going to the left, for the sign of it, you would subtract them from each other. So that minus that gives you 3.05. So that's superposition. The other way you can solve problems like these is with Thevenin equivalent circuits. So you can convert voltage sources with a series resistance into a current source with a parallel resistance. And basically what's inside the dotted box here would look the same to the outside world. You couldn't tell which is which. So if we scroll to the right, you'll see that this small dotted box is a voltage source with a series resistance, is now converted into a current source with a parallel resistance. So the resistor stays the same, and the current source becomes the voltage divided by the resistance. There's your 1.7875 again. Now, to finish solving this problem, we need to take this combination in the larger dotted box and convert it back into a voltage source with a series resistance. That gives you now a voltage of 1.589889 through a new resistance. The series and parallel combination of these three resistors becomes 889. And you haven't converted the voltage source, so that stays at 4.3. And when you run that analysis, that calculation, so 4.3 minus 1.5889 divided by 889 gives you 3.05 again. So that is a way of doing it with using Thevenin equivalence, where you convert between voltage and current sources and back again. Another method, mesh analysis. So you take and draw your loop currents. So every window, basically, you draw a loop current. If you know the direction the currents are going in, you can draw it as I have here. Otherwise, it's kind of arbitrary. The signs will all work out if you do it right. But since I know that the currents are going this way, I drew the current directions that way. So you have I1 and I2. You have, or loop 1, loop 1, and loop 2. Now if you write equations for those two loops, you have a loop that's 14.3 equals 8K, so it's 2K plus 6K, 8K times I2 plus 1K times I2 plus I1, and then back. So the entire, all the voltages in the loop should all add up to 0. So that's why it's like that. Then the other loop is 4.3 equals 1K I1 plus I2. and you go through solving those two equations, and you get 3.05 milliamps for I1 again. And I2 is 1.25 milliamps. As an aside, one thing I did back in the olden days when I was still in school was write my own SPICE program. And I used Fortran to do that. And in order to do this kind of work in a programming language, I used matrix algebra. And so here is how you would take these two equations and rearrange them like I did here and draw them in a matrix format. And you would solve this. Here's a video. I'll put the videos in the description if you want to go through it in a little detail how this was done. But you basically take the inverse of the matrix to get the currents alone on the left hand side. You take the determinant and then you multiply it all out, and you end up with I1 is 3.05 and I2 is 1.25. So matrix math if you want to solve simultaneous equations, linear simultaneous equations. And it helps if there's only one answer. I guess there's the possibility that you could have, equations where there's multiple answers. Gets kind of complicated, but there should only be one answer, and so that makes it a little bit easier. Then finally, nodal analysis. The fact that there was no resistor in series with the diode kind of makes a nodal analysis not quite as interesting. Let me scroll back up, because you'll see you basically end up with no resistor on the left hand side here. The nodal analysis is not as interesting to look at, so we'll scroll back down and let me just see, is this the end? Yep, that's the end. So this is the last thing I'm going to show you. I added a 500 ohm resistor, and you go through the same process, which diodes are conducting and which ones aren't, and you find out that D8 is not conducting. If I click on this, yep, 11.559 volts. So that's with the 500 ohm resistor. This dropped a little bit, but not very much. So the upper diode is still not conducting. So we can redraw this like here, and we have 4.3 because of the diode drop. So we have 4.3, 500 ohms, 1 k ohm, and the combination of those two resistors gives you 8 k ohm. And you write, so you go over here, you write your equations. You know that these three currents add up. So I3 equals I1 plus I2, or you write it I3 equals I1 minus I2 equals 0. And then you write your equations for the voltage nodes. So VB minus VA, VB divided by 1K is I3. VA minus VB divided by 500 is I1. VC minus VB divided by 8K is I2. So you just put in the values for I3, 1, and 2. And then to help further, you multiply across by 8K, and you end up with 8. So you end up with 8 VB, 16 VAVB, and just VC minus VB equals 0. You rewrite that to solve for VB, and you get VB equals 3.32, and I1 is 4.3 minus VB over 500, 1.952 milliamps, which is what the simulation also says. If I right click on that, you can see that I have it, the current through R36. So that is some pretty basic circuit analysis using 4 methods, maybe 5 if you include being able to just look at it. 1, 2, 3, 4, 5 methods to solve some circuits. I just thought when I saw this up online that it might make an interesting, not too difficult circuit to talk about these different methods for circuit analysis. Let's see. Don't ask me hard questions about this. My math is not real strong these days. I haven't done anything really very rigorous mathematically for a long time. So if you ask me something difficult, I probably won't know the answer. But as always, I hope this was helpful. And if not, maybe at least interesting, to where if you see something like this, you'll have some ideas on how you might solve it if you need to. Let's see. Oh, one last thing. There is an interesting video. If I find it, I'll put it in the description too. MIT professor Lewin did a video some time ago saying Kirchhoff's voltage law is wrong or something like that. And he did a demonstration that showed that the same circuit didn't work one way versus the other way. And I think what's interesting about this is these methods of doing analysis are very simplified versions of Maxwell's equations, and they have assumptions in that the fields don't interact in these paper designs. So what do I think? I think if you get one of these where it's not working and you're sure that this analysis was correct, chances are there's some external field or configuration of the circuit that you haven't accounted for. So you can do these, have the right answer, and it still won't work. So you got to be careful. It can seem like black magic sometimes to get these things to work the way you want them to. It's really just a lack of information that causes things to not come out the way you thought they should. So think that's about all I have to say, and I will end the video now. Bye.